So I just wanted to do a little introduction to the lab equipment, and then we'll walk over there and look at it. But we'll be using parts of it throughout the entire semester, from Lab 0 on, and then other parts of it we won't use until later in the term. But it's good to get sort of an idea of what we're working with what our environment is. So let's go to our embedded computing notes, and we'll go to the single file here. And Appendix A is the Embedded Computing Laboratory Appendix, which gives you an overview of all the systems that we're going to be using. Now, currently it's just an overview, but I'm planning to expand the documentation of it. The documentation right now is relatively minimal, but it's going to get more involved. So the Embedded Computing Lab at St. Martin's is a space dedicated to teaching embedded computing and electromechanical systems, hosted in the robotics lab and developed in collaboration with Professor Garbini, like I mentioned, at the UW. To whom credit for much of the design is owed, especially in spirit. Some of the actual equipment is different, but his original ideas, so I want to make sure he's credited for that. The following description is of the apparatuses at ECL, which are similar to those at the UW. The primary differences are that each lab has a different set of motors. Some of the hardware attached to those motors is different. Actually, most of it is different. And the UW uses a custom analog amplifier to drive the motor, whereas the embedded computer lab here uses pulse width modulation, as we'll describe. The developers of the following content distribute it to try to help other people. So I'm documenting it all so that people out there in the world can use this too, and they could build their own. This is actually, I would say, a factor of at least 5, but maybe even more, less expensive than buying like a commercially available system. So it's relatively inexpensive development environment, and it's pretty functional, pretty nice. So the high-level embedded system is the only thing we're going to talk about today. So the ECL has 3 systems for student use. It actually has 4, but the 4th one's not going to be online for a little bit. For some reason, the PC that we have connected to it is not connecting to the network. So each system consists of approximately 4 subsystems, or what we'll describe as being 4 subsystems. So the first is an embedded computer and development environment subsystem, consisting of a National Instruments MyRio microcontroller, a personal computer, and the Eclipse IDE. So the PC and the embedded computer board, they make a subsystem here. So the development environment PC, personal computer, is going to be connected to the MyRio hardware while you're doing the development. So you're writing your code, you're deploying it, that's great. Once it's working and it's deployed, the idea of an embedded computer, of course, is to disconnect it from your PC, and it'll continue to run that program indefinitely. So that's the idea, that's what we're doing. So you might say, oh, well, it's embedded computer, but you have a PC here. The PC is just to initially do the programming. It's called the development environment. And afterwards, we'll disconnect that. 2, the second subsystem is a user interface hardware subsystem consisting of a keypad, an LCD display, and associated circuit boards. So when we've disconnected the PC, we still want to interact with the program. And the way that we do so is through a keypad and we get some feedback on the LCD screen. So when we type things in, we'll see things on the LCD screen. So we actually have to program all that. But this is really, so far, a keypad and LCD screen, these are two of the sort of basic types of input-output devices you would connect to an embedded computer, right? So say you had a really fancy fridge and you could change settings on it. You would do so by having a little LCD screen and change buttons. Or your like Honeywell thermostat or something like that. Similar sort of interface. Very basic inputs, very basic readouts, things that you can use to do rather simple tasks. Okay. And then I'll look at the picture in a minute, but I don't want to give the picture away, because nobody will read this part. So a motor driver subsystem consisting of a DC power supply and a pulse width modulation motor driver circuit board. So that's the thing that's different than the other system. We're going to be using PWM, which there are a lot of advantages to using, and we'll talk about why that is. The primary advantage is cost and also size. So 4, a motor and mechanical apparatus subsystem consisting of a flywheel supported by bearings and coupled to the shaft of a DC servo motor with encoder for feedback. So this is what I did during my lunch. Actually, this is a better resolution than that. Okay, so let's take a look at this hardware a little bit. So in yellow, and also off screen, is the embedded computer and development environment subsystem. So what's not shown in the picture is the PC that's sitting next to this. But in yellow, this is all of the MyRio sort of part of the subsystem. And it includes the board itself. So this is the embedded computer itself, which has on board the microprocessor and also an FPGA, which we'll talk a little bit about, fully programmable gate array, which is blazing fast. We're going to use it, but we're not going to actually program it ourselves. Programming an FPGA is beyond the scope of this course, but it's really cool. So they have built-in libraries we can just use for the FPGA, and we will for the input and output because it's really fast. So that's part of why we're using this board, is that the input-output is really fast relative to, for instance, a lot of prototyping boards like Arduinos, which we'll talk a little bit about Arduinos later, and Raspberry Pis and some others, are sometimes they don't have the performance that we can get out of this board, in part due to the FPGA. Okay, and we have this terminal board here. I'm not planning on using that for this course, but you could do some analog and digital interfacing through these ports here that this gives you. A proto board here, which is just your standard proto board that gives you the pinouts from the side. So the MyRio has 3 connectors with a bunch of pins. So this connector is plugged into this terminal board. Another connector here with, I think it's like 32 pins per connector. This proto board is plugged in there, and it gives you those pinouts so that you can easily solder in a circuit of your own. It's not doing a lot, and we'll discuss what it is doing later on, but it is helping us with a couple aspects of the circuit. So that's basically our embedded computer and a little bit of its interface hardware. The LCD screen and the keypad, they are connected to a custom circuit board designed for this that has a connector that connects to this connector of the board, and so that one is mostly just using the digital I/O, and we'll be using that digital I/O to program what to do when you hit the key labeled 1. For instance, I put the stickers on here, so those are just buttons. We have to tell it what those buttons do. So that's a task that we have. It does not, nothing in that MyRio yet knows that the 1 button is the 1 button. So we'll have to figure out how to tell it. And then you can see like there's an up and a down key, enter key, backspace, minus, negative. This is actually dot for a decimal point. And then the LCD, which is where we get, I think we have 4 lines on this one. So we can display messages. When you enter a 1, for instance, you might want to display a 1. Possibly. Depends, but probably we're going to want to do that. Maybe 2. It's hard to say. We might be feeling just weird, and we might want to switch it up. So that LCD is going to be our main display for the user, and the keypad is going to be the main input for the user. So that's the other that's one of the subsystems. The motor driver subsystem is here. It also incorporates a power supply, which is underneath. So this is just plexiglass, and it's stacked. So there's a DC power supply that's, I'll show you a side view. Where is it? Aha! A side view. Front view. Yeah, front view shows us the DC power supply hiding underneath all of this stuff. That is the one thing that could hurt you in this lab. So it's hidden underneath in part for that reason. It's hard to touch it. So don't go sticking your fingers in there. There's like a caution. So especially this part here, where the leads come off, there's like a caution electric shock sticker there. I mean, you would have to really try to get your hand in there. Just don't try that. It's not on the level of it's not on the level of super dangerous. It's like a computer DC power supply. It's not good. You could get seriously injured or even die from it, but probably you would be fine if you shocked yourself. Just don't. It's better just not to shock yourself. I want us to be safe. The worst outcome of this class would be for somebody to get hurt in the lab. So please don't do something like that, which I'm sure you won't. Okay. So
for the driver, is it come with the DC motor?
So the driver is purchased separately, and I'll discuss how we would go about choosing that later on in the course. But what it is it's a microcontroller of its own. So it's a microcontroller, and then there's some circuitry on there. So it's like an H-bridge circuit. We'll talk about that. It allows you to drive the motor in multiple directions. And it has some protections because a motor is called an inductive load. An inductive load is one that, well, it has a lot of inductance to it. So from our electronics backgrounds, we understand that inductors, if we change the voltage across them suddenly, if we change the currents rapidly through it, so for instance, if you just flip the switch suddenly, that it was flowing current through an inductor, and you flip the switch and you stop the current from flowing, a very large voltage would result across it. So since a motor has coils in it, it has an inductive aspect to it, not a separate discrete inductor, but it's part of the windings of the motor that's inductive. And so you can't simply be flowing current through there and flip a switch, or it will probably damage a lot of your circuitry that's driving it, because a large voltage spike will occur. So in order to avoid that, I mean, there are different ways to avoid that. There are different methods, but some of the circuitry, and we'll talk about what that circuitry is built into this driver board. So this chip on there, the microcontroller that's on there, you can actually buy separately as a discrete item that you could integrate into your own motherboard if you wanted to, develop your own board. What I did for this device is to actually buy it on, they call them an evaluation board. So, and it's made by a company called Pololu. So they make a lot of these. They're really convenient for doing things like this, where you want to build something with a certain chip, a certain microcontroller, but you don't want to have to get a bunch of circuit boards printed yourself. So you don't want to order a bunch of custom circuit boards, because there's always minimum orders, and they're actually getting cheaper, but still you don't want to design it. It's kind of a pain. What you'd rather do is just put in some connectors, maybe solder a couple connectors on there and be done. So they sell these breakout boards or evaluation boards that allow you to use that chip without having to develop a full board for that chip. So really convenient. And as mechanical engineers, it's something that we, when we're prototyping, it makes it very, very helpful for us. We can just order one of these boards, integrate it into our prototyping device, and try it out. And then at the end, if we said, okay, this is the right one after the prototype stage is done, we've tested it out, maybe we'll actually, if you're going to mass produce it, you're going to want to have your own board. But if you're not going to mass produce it, if it's a small sort of system that you're going to build 5 of, you might not. You might just use these evaluation boards, because they often come with all the right circuitry for interfacing it. The protections are on there, temperature shutdown sometimes. Like they're really convenient. If there's a mass production, if it's a mass production product, probably you'll also have an EE person on the team, and then you'll have them design the board for you. They'll design the board. You don't need to design the board usually. I mean, it's something that we can do. I've had some students build boards and get them printed, and they're like, sometimes it's like $100. You can get pretty nice. It's convenient. You can either print one or like 50 for like $100. They don't really, the price doesn't really change that much per unit. So it's just the minimum to get it set up. Yeah, so the driver has got some nice circuitry, but essentially what it's doing is we're using pulse width modulation. So to kind of give you a little bit of an overview, the MyRio, it can deliver pulses of voltage to anything that you want, but it doesn't have much power behind it. So it can't supply a lot of power. It can just supply what's called like a signal voltage. So it can supply enough voltage to interface with some device, but it can't, for instance, supply enough power to drive a motor. The motor requires quite a bit of power. So what we do is we have that separate DC power supply. This thing can supply some power, okay? But it's not a variable power supply, okay? So if, and actually that's one of the main differences between this system and then the system that they have at UW. They have called a linear amplifier. So they can just give it an analog voltage at a small power, and it'll put out a high power voltage at the same signal, at the same level. We don't want to go that route for a few reasons, mainly cost. Cost difference is significant. But a lot of times nowadays, we would prefer to use this method anyways. The pulse width modulation method is actually widely used in a lot of places. Driving motors is only one of them. You can also, even the simplest example is an LED. it's a lot more energy efficient to use pulse width modulation to power an LED versus putting in resistors in the circuit. So anyways, this is a sidebar. Well, so I'll try to come back to this. So you have the DC power supply. It can supply a lot of power, right? And then you've got your myRIO, can't supply a lot of power, but has this variable pulsing capacity. What the driver does is it brings those two together, and you plug in the DC power supply with all of its power, and you plug in the myRIO with its pulsing, and it essentially gates the high power from your low power signal. So you have your low power signal that's pulsing, and what the driver does is it opens and closes with that pulsing, and it lets sort of the big power from the DC power supply flow through and not. So it can switch very fast. The driver also does the H-bridge, which lets you drive either direction. So it's a really nice little circuit. This one, I think the evaluation board is like maybe $30, something like that. I think that the microprocessor, if you're ordering thousands, is like $1 maybe or less. Very, very inexpensive. Really nice. Used in automotive stuff quite a bit to drive motors in, like if you want to say roll your window down or something like that kind of a small motor. This type of chip would do that. Okay, so that's the driver, motor driver subsystem. And then finally we have our motor, okay? So the motor has a face mount. So there are different motor configurations that you can get. We have a face-mounted motor, so you have to bolt it to the face of the motor, and then you have to have a hole in the face mount so that your shaft can go through that. We'll talk more about it. It's a nice little DC motor. They call it a servo motor because it's of rather high quality of a motor. It's not as inexpensive though. So this is the type of motor that you would put in a manufacturing environment, say. Need to run many hours, be reliable. This would be the type of motor you would do. And we're using that in this lab in part because we want to prepare you guys for that manufacturing sort of environment, but also I want this thing to last many years, and I don't want to have to replace it all the time with a new motor. So nice motor. Probably, I think it was $400 including the encoder on the back, which is like $100 of it. So like $300 for the motor and like $100 for the encoder. So the encoder is a rotary encoder. We'll talk more about that, but it gives you the measurements of the position of the shaft, the angular position of the shaft. Because we're going to be doing feedback control, we need to know that. And so that's what is mounted on the back here, this black thing with the ribbon wires coming out. That's the encoder. And then on this side, we have the shaft coming out. We have a flexible coupler, which we'll talk more about why we need a flexible coupler, but essentially you're going to always, when you actually have real systems and manufactured systems, the alignment's not going to be perfect. There's going to be misalignment this way, and then there's going to be misalignment angular-wise. So this flexible coupler allows you to couple those shafts with some play. They don't have to be perfectly aligned. And then the bearings, this whole thing is mounted on a plate. The bearings are supported by this part here. These are custom parts that we did in-house. The bearings are housed in there. There's 2 bearings, one on each side. And then we have a flywheel. So we're driving this load. This flywheel is a stainless flywheel. Pretty good amount of inertia on that. And so that flywheel, we're going to control its speed at different times. We're also going to control its position as well. So those are the two things we'll do with it in terms of control. So that is the main aspect. Yeah, so can't really see much different from this side other than, just a little bit of a different view. There's some rubber feet, and you'll be able to tell once we start running the motors. When you start running these things, you're going to get some vibration, even though they're really well put together. Nothing is totally perfect. You always have some slight misalignment, so that always creates a little bit of vibration that gets transmitted from the motor down into the structure. And the imbalance that, this slight imbalance that can happen gets transmitted. So we use rubber feet on the bottom of this to help to reduce that. We could reduce it more if we cared more, but we don't. So we just let it. It's just the noise that kind of annoying sometimes. There's feet on these as well to give it a little bit of isolation, but not too much. So yeah, so that's the embedded and development environment and the electromechanical system and all that. This is what we'll be working with. For the first few labs, we'll mostly be working with these subsystems and the PC to do the programming. Later on, we'll start to incorporate the driver and the motor and the mechanical side. But only once we get the keypad and the LCD stuff all working together so that we have input and output with the user, then we'll start to include control of an actual system too. So there's lots to learn. I'm excited. I think it's going to be really fun. This is definitely my fun class. This is my fun class. So, yeah. So let's go over to the lab and I'll show you guys the stuff.